So good afternoon, everybody. This is a restart of the seminars of the physics department of Ecole Polytechnique. It's our pleasure today to welcome Stéphane Mallat from Collège de France. In fact, Stéphane is at home here. He was a professor of applied mathematics between 1995 and 2012, I guess. Also the president of the mathematics department of Ecole Polytechnique during 3 years. He then was he's now professor at Collège de France, but in between he was professor of informatique at École Normale Supérieure. So always at the interface between mathematics and informatique. Today it is professor of data sciences at Collège de France. I will not make a list of all the rewards of our colleague, but let me just notice that he is a member of French Académie des Sciences, French Académie des Technologies. He has also made a short trip in the creation of a society. It was Let It Wave between 2001 and 2007, working for devices, fabless devices for television. He was also the receiver of the Grand Prix EADS de l'Académie des Sciences. Well, today he's here to say a word about his work and multiscale interaction between physics and machine learning. I will let Stéphane present his work. Thank you very much.
Thank you for this. You hear me? Yes? So I was thanking you for this warm welcome, and I'm indeed very happy to be back here. And especially in the physics department, because there are very, very beautiful problems and interface nowadays between data science and physics, and in particular with the spectacular results that I'm sure all of you have heard about with deep networks. So that's what I would like to dig in and try to give a perspective on the scientific issues and potentials of all this. So there will be the work of many people, many collaborators that I'll be citing on the way. So the problem basically is whether one can learn physics from data. Of course, we know usually how to proceed with an expert knowledge who will establish a model with few parameters that can be identified from data. But here the question is different. Can we really learn the whole phenomena directly from the data? So what does that mean? If I take several simple examples, one toy models that some of you may know is called 5-4, is a simple toy model used in statistical physics with few parameters that I'll be speaking about, which is interesting because it's in some sense the simplest model where you can observe phase transitions, but you can move to more complex problem. Weak lensing, I'll be speaking a bit about it. That's happening in cosmology when you observe objects which is in the foreground and the light is emitting by the background. Because of the mass of the object, the light is deformed. You are observing these deformation effects, and from that you can compute the distribution or estimate distribution of mass in the universe. There is going to be a new mission called Ecole sent just for that. Questions, can we describe this density of masses statistically and try to relate that potentially to gravity effect? So these are the issue of mass density in the universe, but you have much more classical problems such as turbulence, fluid turbulence. This is a very open problem. Can we describe the statistics of fluid turbulence? Can we relate that to Navier-Stokes equations? And you can go to the scale again of astrophysics and looks at turbulence of gas, hydrogen, heliums, and so on. We can go back to another scale, which is quantum chemistry. There are major issues, of course, to understand whether molecules are stable or not, what will be the value of the ground state energy. Can we regress that directly from data, from geometric information, essentially ignoring Schrödinger equation, or at least getting very few information directly from Schrödinger? So these are the type of questions. And of course, the answer is not going to be forget physics. It's really try to understand what physics can bring in interface with these data problems. So from a statistical physics point of view, if you think of it as a system at equilibrium, what you'd like is to compute the energy which defines the probability distribution of the state X. And in this case, we'd like to compute that from realizations, so several examples of the fields, out of which you would like to compute or define this energy which defines the state of the field. So typically, the question that comes out from this kind of problem is first, try to define models of E of X. As I was saying, the big difference with usual models is that we're not going to have 2, 3 variables, but potentially hundreds of thousands, potentially even more millions. And then the question is, once you've defined such models, how can you optimize the models? So this is the kind of question, building models, optimizing models, that is at the heart of these problems in data science. Now, what has been done is that we now have, and I'll go more into that, techniques to do that with neural networks, for example. But up to now, very little has been done on trying to understand the physics from the kind of things that were computed in these models. The other type of question I'll be asking is relations with totally different problems, such as image classification, which looks very far. And I'll try to show that from a mathematical standpoint, these problems are, in fact, pretty close. So if I begin with a simple example for turbulence, the simplest model you can think of, which is used in physics, are Gaussian models. That means that the probability distribution is defined by an energy, and the energy is quadratic. Mu is going to be the mean. Here you are going to have the inverse of the covariance. So these models have been proposed in particular by Kolmogorov, well-known paper 1941, where he proposed, based on Navier-Stokes equations, to build a model of turbulence which is Gaussian. So here you have a turbulent flow. This is, in some sense, Kolmogorov model, which have exactly the same second-order moments, in other words, the same power spectrum than this image. Same thing for this turbulence here. Here's the model. Now, it captures something, but it misses a lot. In particular, it misses all the geometrical structures. And nowadays, the question is how to model these geometrical structures. So, of course, there has been a lot of work done since 1941. People tried, in particular, to go to higher order moments. This is just a second order expansion of the energy. Why not trying to go to higher order? And that doesn't work. It doesn't work because it's extremely hard to estimate these higher order moments in high dimension, and the regressions give very bad results. So, question how to go beyond Gaussian models and how to compute these long-range interactions without that kind of techniques. And here comes these deep nets. So the deep networks, they are initially mostly used in classification and regression. So the problem is the following. You would like to identify, let's say, dogs from cats, from horses. So you have an index, y, that you want to estimate. But y can also be the energy of a molecule in quantum chemistry. And you want to identify y given the data x. So if you have the conditional probability of y given x, you would pick for y as the most probable value, so the maximum of the probability. So the whole problem of classification is, again, about building models of high-dimensional probability distribution. So we're going to build models indexed by a parameter theta. This is standard approach. The difference of these networks is that theta is going to have a huge number of parameters. How is it built? I'm going to begin from X to be an image. First, you build convolutions, so filtering with very small supports, and you're going to obtain a whole series of images here after subsampling. So the second layer, or the first layer here, is built of images that are all obtained from this one with a convolution, linear operator, translation invariant, and subsampling. This is my first operator, W1. And then all the coefficients, you do something very brutal, which is called a rectifier. You kill all coefficients below 0, and you keep only the coefficients which are positive. And then, after this nonlinearity, you reapply a nonlinear operator, a linear operator, same thing, a convolution. For each of these images, you sum out the result. You're going to get a result here. And you reapply your rectifier. And you do that for many, many different filters. That defines a huge matrix here, which transforms this into this, and the nonlinearity. And you repeat. Each time you subsample, so space is going to become smaller, smaller, and smaller, until it almost collapses. And then you apply a final linear operator, and you get the log of the probability, which is indexed by a parameter theta. What is theta? Is the set of all these linear operators, all these matrices. Now, theta, as I was saying, can have up to billions of parameters. Huge. You are not now building huge networks. So these are your linear operators. Now, how do you choose the particular theta, the particular weights of your network that is going to be appropriate? You are going to optimize it. And the idea is extremely simple. It goes back to a paper of Ronald Fisher, 1923, which basically consists in doing this following thing. You have examples, which are your images xi and the response yi that you want, that you've obtained. And you are going to try to optimize the average of the log of the probability at these points. This is called the likelihood. Basically, you would like to find the parameter of your probability such that the events that you know are true have a high probability. So find the theta, which is going to maximize the log, which amounts to minimize minus log. To do that, you do a gradient descent. It should absolutely not work because you should have plenty of local minima. But the miracle, and it felt as a miracle in the 2010, not only it works, but you get really exceptional results for image classification. Now we can recognize face objects and so on, even better than humans on specialized tasks. Sounds, language, you now have systems like GPT-3 who can write, program, and so on. Very impressive. But you can also do regression in physics, quantum chemistry, fine geometry of molecules, all kinds of tasks like that. And you can also generate fields. And I'll show for turbulence and different kind of example. So now there are plenty of applications. In all physical domains, people try to understand how they can use that with data to predict physical phenomena. But we essentially don't understand, or very little, why it works. And the problem from a physical point of view is that it's essentially used as a black box. And it's very hard to understand what's the relation between the physics and what is being built. And what you would like, given that these things seem to work very well, is potentially to understand better the physics by trying to understand how these predictions were done. So that's the topic. And so what's relation between these network models and physics? And try to see what are some interesting or important elements to understand that. Now, there are several things which are important. You can see that the information is progressively reduced. So essentially, a coefficient here is going to see aggregation of information at very large scale, and that happens progressively. And when you look at the filters here, they look like small waves at the beginning, called wavelets. I'll try to show the relation. So I would like just to show you the kind of results on this example of turbulence that these deep nets obtain. This is one layer of a deep net. What people do, they keep the correlation between two coefficients of, within a layer. And they learn these coefficients by taking real fields and looking at their value on a network that has been learned for some other task. And then they resynthesize new fields. Now, notations. X, in my case, is a field, is a physical field. I know that X in physics is position, but here X is the whole field. So you resynthesize a new field which has the same correlation structure, and look how it looks like turbulence. Although a pure correlation of the field itself, which a Gaussian process would do, absolutely doesn't restore the structure of the field. So why does it work so well? Okay, so in the talk I'm going to first show that this is very much related to the notion of renormalization group, which is a very important tool used all over physics. So I'm going to begin with Wilson renormalization group. That will be the most technical part of the talk, to give you the main ideas, which essentially consists in trying to understand how things evolve across scales. And then I'll show if you modify these renormalization group, you get something that begins to look like a deep network. So it will be a twist or a modification of the renormalization group. And then what we're going to see is that the key elements to rebuild such structure and capture such physical element is to understand how scales interact, how phenomena at different scales interact and model these interactions. Once you've done that, I'll show that you can reproduce that kind of phenomena, and in particular, turbulence. And the last part, I'll show the relation with regression and classification problem, even in images, but we'll look at quantum chemistry. So these are the three parts of the talk. So let me begin with the idea of the renormalization group as if it was described in the 1970s, first by Kadanoff, but really by Wilson. So the idea here is that you have a physical field, which is here, and you suppose that you know the model. So you do know the energy of your system. And what they wanted to do is to try to build a model with reduced number of degrees of freedom. So how do you do that? You progressively coarsen the field. So you get the same field at a lower resolution, lower and lower, by subsampling, okay, and filtering. And you're going to renormalize so that essentially the variation of the field remains of the same order. So the goal now is at each scale to compute the probability distribution of the field that has been coarsened up. So this is going to be defined by a new energy, and you can compute this probability distribution if you know the probability distribution of the field at the finer scale. So you are basically going to track the energies across scales. So these energies, you have a model. You can expand your energy over a potential or a family of potential functions. And the parameters here are what is called in physics the coupling parameters, essentially describe the different nature of interactions within your fields. Okay? Now, what was the key observation of Wilson is that what you can do is to track the coupling parameters when scale changes. And there is one particular phenomena which appears, is that whenever you have a transition of phase transition, so gas to solid to liquid and so on, you have a completely self-similar problem, and these coupling parameters are completely identical across scales. In other words, you have a fixed point. So that's the main idea in one slide of the renormalization group. Now, what kind of physical models you have? Well, you can define a model where you have a quadratic term and what is called a scalar potential, which is going to constrain the value in each point. So here you have a model of your field, which is defined by the two-point interaction and the coupling parameters that you can describe with a polynomial. And this is, here, the famous 5-4 models where you have a Laplacian. And here, the potential of the scalar potential has two well, one in -1 and 1, which are the yellow and the dark point. And if the temperature reaches the transition of phase, suddenly you see very long-range interactions. This is where the phase transition happens. Okay, and you can replace the expansion of your potential. Instead of using polynomials, you can use rectifiers that will be related to the network. Good. So you need to compute this kind of thing. To compute it, when you go from one scale to the next, you need to essentially, to compute the probability distribution here from here, you have to eliminate the degrees of freedom you don't need. And the degrees of freedom you don't need, they are the high frequencies, which corresponds to a field here. How to represent these high frequencies? People are used to Fourier transform. There is a different way to do it. You are going to represent the fluctuations of your field with small wave, with different orientations. And you can build your small wave by dilating them, translating them, so that you get an orthogonal basis. What does that mean? That means that the field at the fine scale, you can decompose it as a coarse scale field plus high-frequency fluctuations that are expressed as wavelet coefficients. And I'm going to show you that. These are the fluctuations that if you recombine with them, you recover that. This is a decomposition in an orthogonal basis. This one, this field, you can decompose low frequency. These are the fluctuations, and so on. So this is a decomposition of your field in these wavelet orthogonal bases. Now, and that's the work that we did with Thierry Marchand, Misaki Ozawa, and Giulio Biroli. We need to do something more complicated. We need to identify the model from example. So what I want to do is to compute my probability distribution from data. So instead, the first key thing that is going to be a twist relatively to what is usually done in physics. Instead of trying to compute the probability distribution of each field, which is very hard, I'm going to compute the conditional probability distribution, the probability distribution of this given the coarser field. But because the finer field is defined from the coarser one from the wavelet coefficient, it's the same thing then computing the probability of the high frequency fluctuation from the low frequency. These are the core, at the core of calculations that Wilson was doing. So we are going to do that kind of thing. That means that the probability of this is just going to be obtained from a cascade of interactions, probabilities, interaction energies across scale. So you take this, you compute the fluctuation, you get this one. From the probability distribution of this one, you get this, and so on. Now, the only thing that I need, and that will be key in these networks, now to compute, is a model of this transition probability distribution, which is going to be defined by an interaction energy, which is going to be parametrized. And that's how we are going to build models. So, in general, and the interesting aspect of this domain is you'll see it mixes mathematics from very different branches and many different ideas. Now we need to optimize. How do you optimize models in these domains? So you have a model of probability distribution that you would like to be as close as possible to the true one that you don't know, but you have data to describe it. Okay? The way you are going to do it is you are going to minimize this distance, which you can do with what is called the Kullback-Leibler divergence, or its equivalent. You are going to maximize the likelihood, which is about what I said before for the network. Try to find a parameter theta such that the data you observe are as probable as possible for the probability distribution, p theta, which you are going to choose to optimize the true one. If you do that, and that's completely classical in statistical physics, you can compute your parameter theta with a gradient descent, which progressively is going to update the theta so that the observable obtained with your model, the expected value, are going to be the same than the observable calculated from the data. So you progressively update your model so that you get the same observable. And the problem is that this can converge very, very, very slowly if you are near a phase transition. And where do you see it? When you have a gradient descent, you compute the Hessian. If the Hessian is badly conditioned, it's never going to converge. And that's where you have the explosions of these operators, like in physics. And this is why renormalization is so important. When you renormalize, you are basically controlling this convergence. That's an optimization way to see many phenomena that appears in physics. And what I'm going to show is that if you now replace this description by a description scale per scale, you renormalize, all these problems disappear. So what's the idea? The idea here is that you basically have a phenomena which takes into account many, many different scales. And in turbulence, if you look at the power spectrum is going to be very large at low frequency, low k, and it's going to decay, like k to the power, certain power, when k increases. So the eigenvalue, which is the ratio between the largest and the smallest value, is going to be, the conditioning is going to be very bad. What you basically do, you slice the problem in different frequency band, and over each frequency band, the ratio of these eigenvalues remain constant. And you only estimate the system on each slice, which is why you're going to get something which is stable. So basically, the whole decomposition across scale can be viewed as a kind of preconditioning, is a normalization, and you're going to get your fast convergence. So if you apply that to 5-4, near phase transition, which is just a toy model to understand, you recover the potentials at different scale, which are given by these parameters that you're estimating. If you are at the fixed point at the phase transitions, all the parameters are essentially the same, which you see here. And essentially, whether you are at the phase transition or not at the phase transition, it doesn't change. Everything converged quickly. Okay, so now that we understand that, we can try to begin to build models. How we are going to build models? What I said, how do you sample from your field? I can show you that quickly. You want to give a sample of a field which is decomposed as a product. What you do is the first thing, you compute a very coarse scale approximation. And that you can do it by sampling. You have a very short range problem. You then compute the interaction, the high frequency fluctuation. You reconstruct this. Then you sample the conditional probability given this. You get this field. You reconstruct. Up, you reconstruct. Up, you reconstruct, and so on. You do everything across scales. Okay, so convergence result, essentially, it's completely flat now. There is no instability. That I'll go quickly. So these are examples of reconstructions. This is a field that comes from the original. You estimate your model, and then you can reconstruct new examples of your field which have the same statistical properties. Now, this was a simple problem because all the interactions were local. If you go in a problem such as in cosmology, you have global interaction because of gravity, which is very long range. So if you see a field like distribution of masses in the universe, you do not hope, there is no hope that your Hamiltonian is going to be local. So the problem now is to estimate your Hamiltonian with global term. Now, in these cases, you can do it because you are estimating essentially the conditional probability at each scale, the energy at each scale, and these global interactions, you are going to build it from local interaction at each scale. And that's what we did. we computed these potential. I'll go fast on this example, and you can do generation. So in some sense, that's the first time that you get a Hamiltonian for these things. And the reason why it's interesting, as I said, is that you want, out of this, to try to infer the distribution of mass out of the properties that you have on the distribution of these, some sense, deformation of light that you observe from your telescope. Okay, I'm now going to move more towards networks. What we're doing now is quite simple. We're just taking the images, decompose it into the average and the wavelet coefficient, iterating that. That was the wavelet coefficient, putting the nonlinearity to compute the potentials across these images, the conditional probabilities. And we use scalar potential. That's going to work for these things. It's not going to work for turbulence, because turbulence have interaction which are much more complex. So the topic you are now facing is to understand scale interactions when the problem is not as simple as 5-4 or as the example of weak lensing. And again, well, see, that's the power of this network. They build very rich models that can take into account very complex interaction. So I'm going to show that on examples. The problem, as I said, is to compute these conditional probabilities. The probabilities of the high frequencies given the low frequencies that you've already been calculated. And that's the same thing than computing the probability of the high frequencies given, or the wavelet coefficient, given the wavelet coefficient at all the previous scales. And you want to build a model of the energy. So, how to do that? Again, the first idea that comes to mind is high-order moment polynomial expansion. This is almost an automatic reaction in physics, because Taylor series. Again, very hard statistically, because your high-order moments have a huge variance. You essentially cannot estimate them. Neural nets seem to be able to do it. On the other hand, you end up with a model with millions of parameters, and you have no idea what this model is about. So the question is, can we reproduce the same kind of result, but with models where you can begin to understand the physics? So not learn these potential, but get them from the expected mathematical properties that you think you can get from the field. So if you look at an example of image where there is some geometry, this is an image with a lot of geometry, you can look at visually the wavelet coefficients. This is the averaged image, and these are the wavelet coefficient. It looks like the edges seen along different orientation. Gray means that the coefficient is 0 because locally there is no fluctuation. You have big coefficients near the edges, okay? If you do that at the next scale, these are the wavelet coefficient obtained from this one. And look, they look very similar, okay? Of course, the edges, they propagate across scale. Again and again. So first thing, you see that you have a very sparse representation. Most coefficients are 0 besides the location where something's happening, an edge or something. Second thing, the coefficients are very dependent across scales. And that's what you want to capture the physics or the statistics of the field. Now, why Gaussian models don't work? You see, these coefficients, they are very dependent, but if you compute your correlation between the coefficients at different scale, the wavelet coefficient at one scale and at another scale, it's almost 0. Why is it almost 0? Because they've been obtained by filtering with a wavelet which lives in different frequency bands. So they oscillate at different speed. When you correlate two things which oscillate at different rate, the correlation is 0. So there is apparently no correlation, although obviously it's the same kind of shape. So you want to express the dependency in a nonlinear way. And the observation is what you need is essentially the zero correlation is due to the phase, to the fluctuation of the phase. So you want to get rid of the fluctuation of the phase and rather look at the correlation of the amplitude of the coefficients. But this is not enough. Phase is also important. Whenever you have a coherent structure, such as a Dirac, an edge, or something like that, the phase is very coherent. So you want to also capture the coherence of the phase. And that's what we're going to do by correlating the coefficient with the phase from coefficients which the phase has disappeared. So we just keep coefficients which are correlations, but not of the original one, after putting a nonlinearity which is very similar to the rectifier, which is a modulus. Now, why do you have this cascade of filtering? The next idea is that your correlations, they are going to be non-zero even at long range. So the correlations themselves appear at different scale. So to capture that, you want to take your coefficients and redecompose it at different scales. So basically, you are going to do a first filter, wavelets, a nonlinearity, another filter, a nonlinearity, and you are going to cascade, like in a neural network. So that's your first decomposition into averages, average, and the wavelet coefficients, the fluctuations. You apply your nonlinearity, and then you redecompose into average and the wavelet coefficients, and you can cascade that. Each time you normalize, like in the normalization group, and then you compute the potential interactions. I'm just going to do it twice for now, okay? And what is the bar which is horizontal? It's the same that the kind of scalar potential. So here it's just going to be correlations, and I'm sorry, also scalar potential, but between the coefficients that have gone through several layers. If I do that, so the only thing that I changed is I did twice cascade of these wavelet transform. And I build models of turbulence, you get very good reproductions. And these models have been built with much less coefficients. The number of coefficients used by a neural network that was learning everything was several 100,000. Here you have 2,000 coefficients. It's not small. But with 2,000 coefficients, now you can describe the statistics of these turbulence phenomena that are decomposed over terms that you do control, which are these wavelet coefficients. So this is an example. This is work that we did with the people in the cosmological group at the École Normale Supérieure, Erwan Alice, Thierry Marchand, and this group. And basically here the problem was to model the distribution of mass that you observe in the universe and be able to capture the statistics in order to reproduce them and to compute an equivalent Hamiltonian. Now, what people also did, this is a different group led by Brice Ménard at Johns Hopkins, is to use these statistics. If you can reproduce the statistics of the distribution of mass of the universe, then you should be able to compute the physical constant. And one of the major problems in cosmology is to have a good estimation of the 6 basic constants that define the growth of the universe, which depends upon the proportion of dark matters and all kinds of physical phenomena that goes well beyond me. And people are trying to regress that. What they showed is that basically from these statistics, you can regress that as well as what you could do from a black box obtained with a neural net. So that means that it begins to be possible to do the interactions with the physics. Let me finish by looking at the relation with classification, regression, and particular image classification. So the problem here is different. You don't want to resynthesize data. You want to identify a new parameter, y, given the data. So it can be a class of an object. It can be, as I said, the energy of some physical phenomena. And I'm first going to do that with the kind of computational structure that I described. So these scattering, wavelet scatterings, where you take your image, you compute the wavelet transform and nonlinearity, you reapply a second one, and then you build everything at the output by an averaging, and this is your operator. So it's a nonlinear network. The difference with the standard one is that you don't learn anything. From prior information, you choose in advance all the filters which corresponds to these wavelet filters. And what I want to show here is that it works, but not for everything. And neural net can do much better whenever the problem gets much more complicated. So that will allow us to see what's the barrier between what you can do from prior physical information and at one point do you really need to learn the representation. So if you like math, you can study the mathematical properties of this kind of nonlinear transform. But there is one which is very important, is the stability to diffeomorphism, to deformation. And that's fundamental also for physics. Because in physics, and in particular, of course, in cosmology, but the turbulence all over, the field has a tendency to deform under the action of the physical law. And whenever you have a deformation, you want your representation to smoothly vary, which is not going to be true if you compute a Fourier transform. It's true with the wavelets because the wavelets separate the scale, and that's essentially what the theorem here says. So the first application I'm going to show briefly is for quantum chemistry. In quantum chemistry, the problem is the following. What you are given is the geometry of the molecule. That means you know the position of each atom, and you know how many charge, how many electron each atom has. In other words, you know whether it's oxygen, hydrogen, what type of atoms you have. Now, what is known from the calculation of Kohn and Sham, who got the Nobel Prize for that, is that you can compute the energy if you have the electronic density. But to compute the electronic density, you need to solve Schrödinger equation, which can be approximated, and that's what they propose, but still requires a lot of calculation. Let's try, okay, before trying to get a solution, what kind of prior information do you have on the problem? Okay, one first prior is that if you index your atom, the energy is not going, obviously, to depend upon the index. Obvious, but has to be enforced. If your molecule is translated or rotated, the energy shouldn't change. If your molecule is slightly deformed, you expect most of the time that the energy is slightly going to change. And you know that you have multiscale phenomena. You have very strong physical, chemical bonds between the different elements, but you also have electromagnetic van der Waals forces, which are long distances. Essentially, if you want to capture that with a small model, what we're going to do is factorize these effects with the very fine scale effect, which are short range, longer scale effect are longer range, by doing these multiscale decompositions. So, one comment. All the properties I just described are the same in images. When you want to recognize an object, you rotate it, it's the same object. You translate it, it's the same object. You slightly deform it, it's about the same objects and so on. Let me show something very naive. You don't know the electronic density. You can represent still your X as the different charges located at different positions. So you represent it with Dirac's. That's your image. Let's do a convolution with a wavelet. So a convolution of a function with a Dirac gives you back the function at the location of the Dirac. So it's as if each atom was emitting a small wave. The images that you see here are the interaction, the sum of each of these waves modulus. So you see an interaction pattern. When the wavelets are very small, they don't interact. That's the wavelet coefficient. When the waves are big, they interact. From these interaction terms, that's what the network is computing, you capture the geometry of your molecule. So you do that on several layers. This is the scattering network. You get your coefficients which are average, which are going to be totally invariant to translation, rotations, and stable to deformation. And then you do something naive. You take a database of molecules where you know your energies, you know X, you know Y, you do a linear regression. So you just learn a linear operator. And then you take new molecules, and you hope that it's still going to work on new molecules. And again, the kind of miracle is that it does work. So these were initial work that were done by Michael Eichenberg, Giorgio Kacharis, and so on. But there is a whole community now doing that with much more sophisticated networks. As long as the molecule is not too big, it's not necessary to learn the network. The deep net does as well as this technique, and the error is smaller than DFTs, which are standard numerical techniques used to regress energies over this kind of molecule. This is true because the molecules are small. When the molecules are getting bigger, deep networks are getting much better. And that's what I want to finish on. Learning. Why it doesn't work when the problem gets more complicated. So to show that, I'm going to move to image classification and finish there. So for image classification, Y here is not the energy, is the index of a class. We're going to do the same thing. We have our network, no learning. We just learn the linear classifier, which is a linear operator, which gives us an estimate of the log probability from which we compute the index. So if you do that on simple model, okay, a simple problem is, for example, recognize a digit, handwritten digit. So what's happening? The digit can have a different position, can be deformed, slightly rotated, and so on. These are the kind of thing that these multi-scale wavelet representation with scale interaction will capture well. And if you do that by learning a deep net or with the scattering transform, it gives you the same result. Same thing for a texture. But if you want to recognize cars, dogs, cherries, these kind of images, and find their class, which a deep net can do, this kind of technique, which doesn't learn the coefficient, doesn't do at all as well. The error is about 4 to 5 times bigger than what can be done with what is called a residual network. So the question that we're facing here is what is learned? And that's the questions whenever you look at these networks, you've learned a huge number of coefficients, but what is the nature of what is being learned? So to look at that problem, that's the work of Florentin Gut and John Zarka, who are finishing their PhD at Ecole Normale. One idea would be, let's open the network and look at the coefficients. And everybody tried that. And if you do that, you are facing 100 millions of coefficients, and it's a mess. It's extremely hard to understand anything, and nobody essentially has been able. So there is a different strategy, which consists of doing the kind of thing we've been doing, which is begin with a small system, try to see if it works as well, that you master mathematically. If it doesn't, try to complexify progressively. But what I just showed is if you use a representation which doesn't learn anything, you are not going to do as well on these complex images. So then the idea was, okay, you decompose your coefficient with a wavelet transform. But we've seen that for physical phenomena, even for 5-4, for turbulence and so on, you need to learn or to know the interactions of the images across scales. So these horizontal interactions. And at the next one also. Now, in physics, problems such as turbulence and so on, these interactions, we essentially could compute them with correlation. In this case, this interaction is going to be computed with a totally unknown linear operator, which is going to be a convolution that's called in this neural network a 1-1 convolution. And we're going to let the network learn them. So the only thing that we're going to learn is not the spatial filters. All the spatial filters are wavelets. They just expand at different scale. But we are learning the interactions across scale. And out of that, we do a linear classification. So it looks something like that. The filters here are always wavelets, but across the different bands here, you learn the interaction. You learn a filter, and then you put your nonlinearity, and so on. And you do a gradient descent in order to learn all these potentials. So, as I said, if you do a scattering transform and you compute it, you compare it to a neural net, the error is about 4 times to 5 times bigger. So you are totally far out. If you learn just these linear operators across the channels, but maintain the wavelet, you reach the same precision. So what that means is that all the information is within these potentials across these images. In some cases, as I showed you for the very simple cases, 5-4 and partly for turbulence, we can understand the nature. Now the problem is, what is the nature of these kind of interaction potentials across these images, across these scales? So I'm going to finish on that. The morality of the story is that one very important element that clearly appears in these networks is understanding the interactions across scale. And this is not big news in physics. In physics, we know that very well. We know that whenever you have an n-body problems with many particles interacting, factorizing the problem at different scale, that's what we do when we separate quantum chemistry from cosmology, from astrophysics, from and so on, material science. Separating even physics in these different fields is already a scale separation, okay? And of course, these scales interact. We know very well that you have macroscopic phenomena which are due to quantum effect. So there is a propagation across scale. And the whole question, well known in physics, is to understand these scale interactions. So it's about building these models of scale interaction. And from that point of view, the renormalization groups appears very naturally, because it's essentially the tools which helps us to understand these interactions. The only thing, and the twist here is important, is that contrarily to the renormalization group, you don't try to look at what's happening at a given scale or at the next scale. You try to look at the interaction between two scales. That means conditional probability distribution. That means interaction energies. And if you do that, it seems like you can go quite far, and that even with physical priors, you can build models without needing to learn these networks. However, and that's, I think, one of these very fascinating aspects of these networks, if you begin to learn these potentials, you get incredibly complicated phenomena. You can model language, you can model perception of images, audio, and so on, and quantum physical phenomena with very large size or relatively large size molecule. So why? No idea. There are many very interesting problems behind all these things. And I'll stop here. Thanks very much.